All right, well, thanks everyone for sticking around and spending your Saturday morning here talking about Mars. It's one of my favorite topics, so this should be a fun day. What I'm going to talk about today, I just want to take you on a journey, really, from Earth through to Mars, and take you through some of the thought processes that we've been going through, trying to consider where would you land for Mars. And I'm going to take a sort of different tact and try and combine the human exploration interests with the scientific exploration interests as well. There's some error here, just a second. Okay, so you've heard a little bit. Here's your little primer in the NASA bureaucratic structure. So NASA is broken down into two directorates that we care about for this purpose. SMD, which is the Science Mission Directorate, and HUMD, which is the Human Exploration and Operations Mission Directorate. And of course, SMD is focused on science. We've heard multiple talks about the science, what we want to learn about Mars. But then there's also the HEO side, which is what I think a lot of us here in the Mars Society are interested in as well, and that's sending the humans to Mars. And so if we break it down, I think that they two actually go hand in hand. And there's a phrase that's been uttered many times, that exploration enables science and science enables exploration. So I think when we're thinking about Mars exploration, it's a good thing to do to consider the two together instead of always considering them separately. So where would we want to go to Mars and why? Well, I'll try to convince you that studies of the ice-rich subsurface on Mars are critical for several reasons, for both science and for human exploration. We've heard a little bit about this earlier today as well, so there's a common thread, a common theme coming through here. But we have the MEPAG goals document, it's the Mars Exploration Program document telling us goals 1 through 4, what we'd like to do at Mars, and goal 1 is focused on life. Characterize the present habitability and search for extant life on Mars. It actually says that. And if you go to ice and you study ice, that's a pretty good place to do that. You can preserve organics, biogenic compounds, et cetera, and have the potential for some long-term preservation of what we're looking for. And also water is a source for the biologic activity, as Carol was talking about earlier. MEPAG goal 2 is climate. Characterize Mars's present climate, atmosphere, and climatic processes. And ice stability is very dependent on the climate. And you can tell a lot from looking where the ice is, where it's stable, where it has been. That will tell you about the climate itself. And 3 is geology. Determine the nature and evolution of Mars geologic processes. I'll talk a little bit in this presentation about surface geomorphology and how that can actually affect and influence the ice distribution and stability. Because we look at geomorphology a lot to understand what's going on in the subsurface and where ice may or may not be. And then there's also goal 4 of MEPAG, which is prepare for human exploration. And the human exploration group at NASA has put together a document of what we call SKG, Strategic Knowledge Gaps. That's basically, what do we need to know before we can send humans to Mars? And several of those SKGs focus on identifying and characterizing water resources. So, for example, assess the shallow water ice properties and occurrences as a potential raw resource for ISRU. And search for extant life on Mars, because there are issues pertaining to biohazards and also planetary protection issues that Carol talked about too. So there are a lot of different reasons why we might want to go and study subsurface ice for both science and human exploration. So to look at this in a little more depth, what I want to walk you through today is looking at ice stability and the depth to ground ice, because that's pretty important. We have to know where it is and how deep it is if we can actually access it. Look at polygon characteristics. These are some of the geomorphic manifestations of subsurface ice that we can see even from orbit. In geomorphology and ice types, we can try and see, okay, so from what we see on the surface, can we actually characterize what kind of ice we have below ground? And then walk you through a Mars landing site selection process that we went through to try and see, is there a good place on Mars? Are there any places better than others for trying to merge the science and the human exploration objectives? So to do this, what I want to do is just take you on a little trip through the Antarctic dry valleys. Because a good way to do a lot of this is through Mars analog studies. And I know many people in this room do Mars analog studies. There's like pictures of it right behind me. And so for this particular case of looking for ice, the dry valleys are a very good place to go and do this. And so just to get everyone oriented, here's Antarctica. Down at the bottom is the US base, McMurdo Station. And just across are the dry valleys, which are one of the few ice-free regions of Antarctica. And the reason we go here is because it is such a superb Mars analog. It's very, very dry. It's a desert environment. It's very, very cold, averaging about -20. I'll show you some data to support this. Of course, pressure is not a Mars analog because we are still on Earth, so it's important to know the limitations. But I'll show you some data to show why this is really, really a good place to go study subsurface ice with its relevance for Mars. Here's just a little graphic trying to show a little bit why we go to Antarctica. So you have drier conditions on this axis, colder conditions down here. Here's Mars about 5 million years ago. Here's Mars today, super dry and super cold. And you can do work in the Arctic, and I've done a lot of work there as well. It's pretty cold, it's pretty dry. But as you go up into Antarctica, especially the coastal Antarctica, and then moving up into the dry valleys, you get progressively colder and progressively drier. And so you're becoming more and more Mars-like. And that's really important if we're going to look at ice and ice stability. So in particular, here's where we go. This is University Valley in Antarctica. It's a hanging valley above Beacon Valley, which is famous in its own right. It's a bit colder than Beacon because we're at a higher elevation. And we have the presence of dry permafrost and also ice-cemented ground, which is very familiar from what we see on Mars. So just to get some terminology here, when I say permafrost, that's ground that stays below freezing. So your temperatures are always below zero. And you can have dry permafrost, and you can have ice-cemented permafrost, whether you have ice there that's solid or it's just dry dirt, basically, that's still very cold. You can also have an active layer, and that's the upper portion of the soil that actually gets above zero in the summertime. So you can have temperatures that are above freezing seasonally in some places. So, for example, in coastal Antarctica and the Arctic, you do have an active layer. So the upper layers, if there's ice or water there, it's melted and it's liquid and there's mud, and that's very fun for other reasons. But the interesting thing is when you get to Antarctica, this is the only place where you have the dry permafrost. And we have dry permafrost on Mars too, and so this is a very important consideration. So you can have an active layer up in the top. You can get above 0 degrees. I'll show you where we go. It's okay because there's no melt there because there's no water there. And then you can have different types of ice underneath this dry permafrost. In some places you have buried massive ice, which is like basically pure ice. It's like ice cubes. You see that down in Beacon Valley. The upper dry valleys, we have large columns of this dry permafrost. We have ice-cemented ground under there. So there's different configurations that you can have. There's different types of ice and different ways that it can be layered. But the important thing is that it's only in Antarctica. It's the only place on Earth that we have dry permafrost, and that's what we have on Mars. And that's why we go there. Here's an example, because we know that there's dry permafrost on Mars. So here you've seen this picture many, many times, I'm sure, but showing ice-cemented ground at the Mars Phoenix landing site, and you had to scoop away that dry permafrost layer. So that's the configuration you have on Mars: dry permafrost, dry dirt basically that's below zero, and then ice underneath that. Another consideration, Carol already explained this to you, so I'm not going to dwell on this, but on the order of 5 million years ago, at high latitudes on Mars, you had much more summer insolation than you have now. And so Carol has already explained that story, that in these high obliquity periods, you can have melt at these mid to upper latitudes on Mars. And that's very important because this is a source of relatively recent liquid water that you could have on Mars, which would make that area habitable and a very good place to go and do life detection, as Carol already pointed out. So, great. So we have ice on Mars today. We know that in the past, the relatively recent past, 5 million years ago or so, you could have had possible melting. So what this is telling us is that, okay, in these mid to upper latitudes on Mars, we have near surface ice. I mean, we've scooped down to it, we've seen it, we know it's there. And I'll show you some other evidence to show that it's there as well. So you have near surface ice. We have relatively low elevation because you're in the lowlands in the northern hemisphere. So you're above the triple point, so you could have liquid water that could be stable on the surface. And summer temperatures are cold now, but may have been above freezing about 5 million years ago. So this is the rationale, and this is what is underpinning the Mars icebreaker mission concept that Carol explained, is that the Martian Arctic may be one of the most recently habitable locations on Mars. So it's a very interesting site to go to, and something very interesting to think about for future Mars missions. So I mentioned that we go to University Valley and we go to Antarctica because it's a very nice natural laboratory to try and study and understand the ice. And so what we do, we've gone, this is University Valley up here, that's the bigger Beacon Valley up in there. And so what we did is we measured how deep is that ice in University Valley. So we dug pits and we stuck poles in the ground because it's all very sophisticated NASA research. And so what we found is that there's a gradient. Basically, at the head of the valley, there's a big snowpack, and the ice is very close to the surface. And then as you go down the valley, away from that snowpack, the ice gets deeper and deeper and deeper and deeper. So there's this very nice natural gradient, which makes it a very nice natural laboratory to study subsurface ice. And so we put out all sorts of instrumentation. We put out a weather station to measure all sorts of things. I'll show you some of the data that we've got back from that. We put out sensors to look at in the subsurface to get temperatures, at the surface, in that dry permafrost, at the ice table boundary, inside the ice, because we wanted to see how good of a Mars analog is this and what's actually going on over the course of a year. So here's some of the data that came back from University Valley. This is solar radiation, which is not surprising. This is as it should be, but it's important to know the radiation levels for some of the climate, or for some of the ice stability modeling. So in the summertime, you have radiation, and then in the wintertime, it's completely dark. And so we can get, minimum, maximum, average values of the radiation. And then we look at the temperatures, which is also interesting. So this is air temperature as a function of time. And I've added a line at the 0 degree mark so you can see when you're above freezing and when you're below. And you can tell just by looking at it, you're always below freezing. So it's very cold, which is good for a Mars analog. We never got above 0, and our average temperature was about minus 22 C, just to validate what I told you earlier in the talk. We also looked at the surface temperature. And so what you can see, this is right on the top of the ground, basically. And so you can see that at the top of the ground, you actually can get above 0 degrees. That dirt can actually get above 0 in the summertime. And so that's where that active layer comes into play. However, we're at the top of the dry permafrost, so there's no water here, so there's nothing to melt. So even though these temperatures at the surface can get above 0, there's no liquid phase because there's no ice there to melt. The ice is all deeper. Here's in that dry permafrost. So now we're looking just below the surface in that dry permafrost layer, that dry dirt essentially. And again, you can get a little bit less because you're getting some temperature damping as you go deeper down. But you can still see you get a little bit above 0, and we expect this on Mars too. But again, there's nothing here, there's no water here, so there's nothing to melt. So even though you're getting above 0, it's still just dry dirt. And you got up to a whopping 3 degrees C. Here's looking at the relative humidity in that dry permafrost. So you can see you get the lowest values of RH in the summertime. That's when things are very dry. There's not much moisture around. You get higher values in the wintertime. That's when it's dark. You can get some snow that's blowing in that can stay on the top. So you'd expect that trend. I'm just going to skip this in the interest of time. Here's where the interesting part is, because we wanted to know, okay, are we getting any melt in University Valley? Because we wanted to try and see how good of a Mars analog is this for current Mars. And so these are the temperatures right at that ice table boundary. So that's where the dry permafrost hits the top of the ice. And as you can see, we never get above freezing. We have a peak high of about minus 10. So what this is telling us is that where the ice is in this region in the dry valleys of Antarctica, we're never actually melting any ice. So we're never getting any liquid water melt. And then just to prove it even more, if you go deeper into the ice, so this is, we just drilled into the ice and put our sensors in there, and you can see it's even colder, and you're not melting anything. So the dry valleys are a really, really good place to go and do studies if you want to look at ground ice on Mars. Okay, so after running through sort of those data sets, I want you just to remember that dry permafrost overlying that ice-cemented ground is unique to Mars and to the Antarctic dry valleys. So it's the only place that you can go to do this type of work until we go to Mars. University Valley in Antarctica shows a trend with increasing ice depth from the distance, going down the length of that valley. So you've got this nice gradient of ice getting deeper and deeper and deeper. And we're going to learn a lot about ice stability and geomorphology on Earth and Mars from these types of terrestrial analog field studies. I already said that. Let's skip there. Okay, so what can we actually learn? So when you look at University Valley, here's a picture of it looking up the valley. There's that snowpack I talked about. This is about 1.5 kilometers down. You can't see it very well with the lights in this room, but you can see little patterns on the floor of the valley. And so all of this white, these are little cracks that are filled in by snow. And essentially all these little cracks are outlining polygons that cover the bottom of the valley floor. And so polygons are also seen on Mars. What are they? So here's a picture here that you can't see. Here's our tents for scale, so this is about the size of our tent. This is the floor of University Valley. And then here's a picture, a high-rise picture of Mars, showing lots and lots of polygons. Polygons, we have lots and lots of pictures of polygons on Mars. And what they are they're polygonal pattern ground, which forms through seasonal thermal contraction cracking. Basically, you have ice underground that expands and contracts, and that tends to produce cracks on the surface. And so by looking at those cracks on the surface, you can then infer that you have ice, or at least at some point you had ice below ground. So this is one of those clever ways where we can use orbital imagery to try and infer what's actually happening beneath the ground on Mars. So to do a little more quantitative analysis, we decided, okay, well, let's use University Valley as this analog and try and do some actual studies and see what we can learn there that we can then apply to Mars. So one thing that we noticed looking at University Valley is that the size of the polygons change as you go down the length of the valley, right? When you're up near that snowfield, they're pretty small. You can walk across them, and then you go further down the valley, and they get a little bigger, and then down at the end of the valley, they're the biggest. And that's interesting. And then we thought, well, wait, we just measured that the ice gets deeper and deeper as you go down the length of the valley, too. So is there some correlation between the size of the polygons and how deep that ice is? And if we can have a quantitative assessment of that, that would be really important, because then we could apply that to Mars and figure out just from the imagery how deep is that ice. And we really want to know how deep that ice is, because Carol needs to know how far to drill with Icebreaker. We need to know how far down we have to get the ice for human exploration. There's a lot of reasons to want to know where that ice is. So what we did is we just measured the size of the polygons and just showed that they get bigger as you go down the valley. And then we correlated that at the same scale with the depth of the ice and showed that the ice gets deeper as you go down the length of the valley. And then we called up our good friend Mike Mellon, who spent his whole career modeling ice on Mars and Earth, and said, Mike, do you have a model where you can predict the size of a polygon? And he said, let me work on it. So he did. And so essentially, what you're looking at is, on this plot over here, the stresses that are induced by different depths of ice. So I don't have a pointer, do I? No, I don't. So what you see here, these different lines are different ice table depths on this curve. This is how big your polygon is. So these are bigger polygons going down this way. And this is basically how much stress you have induced. And where the dotted line crosses the solid line, that tells you your ice table depth and how big your polygon is. So the takeaway message is that if you have deeper ice, you have bigger polygons. It kind of takes more stress to kind of break those apart. If you have ice closer to the surface, you have smaller polygons. That's essentially what happens. So, okay, that's good. Oh my goodness, okay. So that's good. So we can say, okay, we can figure out how deep the ice is based on the size of the polygons. We can also do a little work to say how old the polygons are, which means how long has that area been stable and how long we've had ice there. So in University Valley, you have pretty well-developed polygons, basically. They're very nice, they're very equiangular, they're very nicely made. And that tells us we had to have a stable condition to make those polygons over the duration for however long that takes. And it turns out that we know that it takes about 10 to the 4 to 10 to the 6 years to get to mature polygons. So we know that, at least in Antarctica, it must have had a relatively stable climate for at least that long to make those. So that is actually interesting and is spurring some other work into some climate change studies and looking at what's been going on in Antarctica. If we look at Mars, in particular the Phoenix landing site, because this was important for Icebreaker too, it's a different story, because it's not so nice and pretty like in Antarctica, where you have this nice natural gradient. But actually, we have all different sizes of polygons that are all intermixed, superimposed. And so that's telling you that there were multiple episodes of polygon formation, multiple different varying ice table depths as these things were forming. And so it was not such a nice quiescent climate at the Mars case compared to the Antarctica case. I'm going to skip this in the interest of time. So, okay, what else can we learn by looking at the surface to try and understand what's going on below ground? Well, there are all sorts of different geomorphic features that have been identified in paraglacial or very cold environments. Cracked rocks, pitted rocks, rocks that are on top of each other. We've already talked about polygonal ground. And I think that I've hopefully convinced you, polygonal ground can tell us something about what's going on in the subsurface. These other things that have been identified and you can see really aren't related to what's going on below ground. It's really weathering, erosion, surface activity. so not so relevant here. So what we really need to do in order to really get down and ground truth what's happening is we need to do some drilling. You actually have to get down and touch the ice. You got to get the samples. Both Carol and Deborah were alluding to this today. You want to actually get there and get it in your hands or in your robotic system, because there are some things you just can't tell until you do that. So in thinking about, well, where might you go for landing sites, this is an eye chart. You don't have to read the words. But the point is, on this side are the MEPAG science objectives, SMD science. On this side are the human exploration objectives, the SKGs, the strategic knowledge gaps. And the important thing is, where there are colors here, that means there are measurements that can be made that fulfill both the science needs and the human exploration needs. So it is not a null set. We can actually go and do a mission that addresses both science and human exploration to help advance both of those goals. One possible way to do that, there are many mission concepts out there. One possible way is the icebreaker mission, so I thought I'd mention that since you've already heard about that this morning, and so you have that in your background. I don't need to dwell on this because Carol already explained it all to you. And so for an icebreaker type mission, you need to go where there's ice for both science and human exploration reasons. And there are two places on Mars where there has been direct evidence of ice. Phoenix landing site, we already scooped down, we saw it. We've already talked about that. And then there's near Viking Lander 2 site, the mid-latitude ice site. And let me just quickly show you some of the evidence there. Here's polygons associated with VL2, probably suggesting that there's subsurface ice there. And then, if you haven't seen these, I think these are some of the most interesting discoveries in the past few years from Mars. These are high-rise images that were taken, and these are recent impact craters that have happened during the time that HiRISE has been in orbit. And what you're seeing is ice that's being exposed from those recent impact craters. And we know it's ice. We have spectra that shows it's ice. We have HiRISE data that's showing it's ice. You can see it actually sublimate away over time. So here's a couple images where you've got these two impacts that are exposing the near surface ice, and then over time they go away because the ice is not stable there. Here's just a map showing where those sites are. Here are the different sites. Here for reference is VL2 over near Utopia. And the ice that's being exposed is not that deep, like 0.5 meter to 2.5 meters. So we're talking near surface ice. So now we have more evidence at even lower latitudes that there's near surface ice. And this makes the human exploration community very happy because they're not so thrilled about the idea of sending humans up to the Martian Arctic where they're going to be in darkness and cold and covered in CO2 ice and all those things. They'd prefer to be closer to they'd prefer to be at the equator. They want to maximize their sunlight, they want to use power, the thermal environment's more benign. So if we can find the sweet spot between being close to the equator for the human exploration, but being at a high enough latitude where you have near surface ice, that could be useful. I'm going to skip through a bunch of these and just say that, so what we decided to do is find out if there is a place that might be amenable to both needs. And so we decided to look in this region of interest near where these exposed craters had been reported. And we decided to go and say, okay, well, is there a spot here where we could conceivably land? And we used the VL2 site as a baseline because we've been there. We've got orbital images. We've got images from the ground. And we decided to see if there's any better spot that we could land. And the things we considered were the presence of polygons, because that'll tell you if there's ice or not. If you have rough topography, because you need a safe landing spot. Ditto for rock density and boulders and craters. Avoid all of that bad stuff. And so went through and looked at all of the high-rise images in each of those and basically categorized each of those categories. Green would be yes, so yes, you had polygons. Yellow would be marginal, there's some, maybe not so much. And then red would be no, no-go, not a good spot. So just keeping it very simple. And we have a paper published on this if you'd like the details of how that was classified. So basically we made maps like this for each of those categories I explained. Green is good, yellow is okay, and red is don't go there. And the goal was to see, is there anywhere that has all green spots? So here's for polygons. You can see there's a bunch of polygons near VL2. There's a bunch over here near Site 5 where the exposed crater was. Topography, kind of scattered, mostly greens. There's some red over by Site 1. Boulders, a lot of green. Most of the boulders are near larger impact craters. The presence of rocks, actually VL2 is pretty rocky, but there's a lot of green down over in here. Looking for the definition of the polygons, so sort of how recent and how fresh are they. In the presence of big craters, there's just a few scattered big craters in that big plain up there. In the presence of small craters, those are pretty randomly distributed. So what we found out is near Site 5, where this exposed impact crater was, turned out to be a really excellent spot. We had really nice polygons, you didn't have too many rocks, the topography was relatively smooth and flat, you didn't have too many craters to avoid, no really large boulders. And so we just wanted to go through this exercise and then give you something to think about. If we wanted to try and merge the science and the human exploration, maybe this might be a good region to go and try and look at. So to conclude, since I'm over time anyway, I think that high priority science can be accomplished by studying in situ studies of Martian ground ice, and for all of these reasons that we've been discussing all morning long. Preparing for human exploration can also be accomplished at a site of known ice occurrence, again, for all of these reasons that we've been discussing all day. And there is a potentially viable landing site within the VL2 region that has even fewer landing hazards than VL2 had, and has direct evidence of near-surface ground ice. So with that, I should probably stop.
We have time for one quick question.
If budget and payload allowed, with what you know now, how deep would you want to be able to drill on Mars?
Well, it depends on where you go. Depends on your landing site.
Sites that are your favorite sites that you're looking at?
I would say at least a meter. 2 would be great, but at least a meter. Okay, thank you.
Thank you very much.